C'est bon? Okay, so welcome back. So in this second part of the practice, we will focus on a key point when you want to run your code on GPU, which is transferring in general, if you want to use an efficient GPU, it's what we call, let me remember, a discrete GPU, meaning it is not integrated with today, not integrated with the GPU, and it is a GPU which has its own memory. And so one of the challenges when you want to use those discrete GPU is to move your input data to the GPU, make the computing, and then move the data back on the host. And it's why also for some problems, it is not worth. If you are not computing enough things, the time that you lose when moving the data to the GPU is greater than the time you save computing there. So you need to try to find a good balance and to check that your use case is worth to be used on this kind of GPU, because you lose time moving the data, okay? So we'll see now different ways to handle this move of data. And so the first step that we will investigate now is to use the shared malloc. So that's in the original cycle, cycle 1 dot things, you just have the buffers on accessors. And starting with cycle 2020, we have this new unified shared memory, some new ways to allocate data and move the data. And the easiest one, which is called lazy because it's easy, but not the most efficient, as we will see probably, is the shared malloc. And then the idea there is that instead of doing a usual new, as I've shown you in the slides at the beginning, instead of doing new, you will do malloc shared, which return you something which look like a usual pointer, but which is usable both when running some code on the host or when running some kernel code on the device. And it's the underlying system that will detect when you follow your pointers to get to the data, that will detect if the data is there or not on the GPU or on the host, and will move it automatically to make it available. And so you do not need to care. It's why we called of unified shared memory. It's just like there was a single memory and the system on the way is doing the move for you. So the idea of the step 2 is that you can have a look at those square buffers and square shared examples, and you use it to transform the starting code, which is in step 2, donc step 2, SRC, Grace code CPP. You take it as a starting point, or your own code if you have make your own project, and to replace the data allocation with malloc shared. A point there is that once you do that, you will need to put call to wait in the right places. Because before, with the buffers and accessors, the runtime system is doing it for you, waiting at the right moment. But once you are using malloc shared, it does not do the job. It does not know when you want to read, when you want to write. So it's your job to wait at the right moment. And remember, every time you submit a task to a queue, you get back the end immediately. It's asynchronous. The job will start on the device, but you do not know when you do not wait for it to be finished. You get the end back immediately. So when you need to be sure that this task has been finished, you must call wait. So that's the exercise now. Replace malloc free or new delete in your code with SYCL malloc shared and SYCL malloc free to give the memory back. Remove the buffers and accessors, etc. And if needed, if you think it's needed, add wait. And check that your final number analyzed has not changed or you have broken something. A few clues that are worth mentioning is that one nice thing with the buffers and the accessors is that they handle for you the dimension too. But with the row pointers that we use with malloc shared, we are back to the real C++ world where we do not yet have the 2D indexes. So you will have to compute yourself if you are in a single memory area and you want this row and this column, what element it is. Because this work which were done by the buffers and accessors before are not anymore done for you. So you have to compute, which is quite a typical exercise when you do this kind of code, but it's a pity that you need back to do it yourself. I guess at the moment we will have MDSpan in C++ finally implemented somewhere, so that we will have multiple index available also. But in this exercise, I think we do not have a MDSpan yet, so you have to compute your index yourself. And also, if you wish, since we do not have those buffers, stories with delayed crash, etc., I think it's better to move back U1 in the process image. It will be more clean. So please try. I'll let you 10 minutes to try this, and then we'll comment the solution. And we'll see, you will see on your machine, and we'll see on Cassidy how fast malloc shared is performing or not. So the example with squared buffered, so just doing an array of size 10, so a queue from a GPU selector. I'm filling my static array with the values, doing buffers on top of my input and output static arrays. And then I submit a task doing the accessors. And finally, the parallel for on the elements to square them. Then I print the result, and I access them with my host accessor. So with the host accessor, I'm sure that it will wait for the computations above to be finished, display the result, and that's all. So the same with square shared. The queue was before. Now, instead of doing static arrays, I'm calling malloc shared for the given size. Filling the input size with my usual values. And then, because I do not need buffers, accessors, I can directly call Q parallel for, where I'm giving the range I want to loop on. Then the lambda, which is done directly using my pointers. But before printing the result, I need this Q wait, or the program will directly send the parallel for and then print before it is computed. I do not forget to do a cycle free for each cycle malloc shared, and that's all. Very simple. So on your side, with Grayscott, the more problem you have will be to compute the index, because you are moving to 2D. I have a question for Joël. I was thinking in this exercise, we compute the index. We compute the index by yourself quite easily. You take your column numbers plus the row numbers multiplied by the number of columns, etc. That's something we are doing very often. So I do it in the exercise, but I think in SYCL, I guess they have made a few functions for this. You know about?
You have get linear ID and stuff like that.
If you want to avoid to code it yourself, I think SYCL is providing a few a few
But
utilities for that.
you have to call it directly on the ID object or whatever.
Sorry?
You have to take an ID object explicitly,
Yeah.
and then you can call that.
Yeah, so you can avoid to compute it yourself. We do it so often that we don't care, but if you're not at ease with that, SYCL is providing a few utilities for this. I should use them in the solution, would be better. If you have succeeded to make it, please tell us in the channel in Discord, does it go faster or slower than buffers accessors on your machine? I'm not sure that there is a single universal answer.
For me, it's a bit slower.
A bit slower.
Yeah, but like 5%, 10% slower.
Yeah, so it's not a definitive result because depending so much on the runtime, but for me too, as we will see. For me too, on my benchmark machine, isolated machine, I can see the same. Okay, we have 2 yes. So let's go forward a little. But we have time, so don't worry. You can go on trying. So a comment on the grayscotesol.cpp in step 2. So my main, as usual, print compiler, look at the arguments. Now I have the new one, this device type, so that you can runtime choose I want CPU or GPU. My construction of queue, depending on the command line arguments. For the arrays, which are the arrays with no border, that only stay on my host machine, I don't need to do malloc shared. I will do malloc shared only for the data which is moving from the device to the host, which are the images with the border, okay? So the usual one, I still goes on with new real as before, fill them, etc. Then I call my process images. So let's move there. So there I'm initializing my magic number, then preparing my U1, V1, U2, V2, which are the data that will move back and forth with the device and the host. So there I'm calling malloc shared of reroll. The number of elements is the extended number with the borders. You will notice that I need this Q argument when doing the malloc shared. So I'm saying this data will be exchanged with this Q, which is connected to this given device. And then I can fill with my real number and then insert. We take the values from my host arrays and put them on U1. So there with stdfill, which is a standard algorithm of C++, or insert, which is a function I have written before, they are waiting usual pointers. I give them usual pointers, and I use them as if it was the same memory between my CPU and my GPU. So there I'm writing there my initial values and call, start my loop on the images and call iterate. And iterate, I give them my U1, V1, etc. So let's have a look at iterate. So iterate before was receiving buffers. Now it's just receiving pointers and use them directly. There you see I'm using input U, input V, etc. as I would use any kind of pointers. There's nothing special. There's no buffers, there's no accessors. And when I'm reading there the input U, the underlying system will see, okay, I need this data that was written before on the host. I will move it from the host to the device to make it available on the device. All without any control needed from me, it's automatic. So my usual work, but then that is new. Before the swap, before swapping my pointers, I wait that the current iteration is finished. If I don't wait, I will swap the pointers. At the same time, the device is working on the memory, the system on the line will get mad. So this weight there is very important. And because I have this weight also, I know that in my process image loop there, I know that when iterate is finished, the computing is finished, and I can extract and I can analyze, no problem. So back to the slide, or I could try to run it live. Quite funny. So I'm in step 1. No, I'm in step 2 now. Step 2. So this command, this script is running the initial code, so with the buffers accessors. So as I said before, I run it 6 times actually to be sure that the on-the-fly compilation is finished and to look for the mean value. And if I want to run the solution, if you use the same script as me, you have to give it more information. You must say, I want to run, I'm using the CMake ICPX CUDA. I want to run Grayscott Sol, and I want it on GPU. And this one will run the solution. And normally we can see that the first one is longer. You see that there, the first one is 1 second and 60 milliseconds, and the following one are rather close to 900 milliseconds. So we see the effect of compilation of the fly. So that back to the instructions. So we'll remove all buffers and accessors, add the needed weight, make some malloc shards. I did not comment on the computing of the index. Let's go back there. You will see there that I think it's in iterate. Yeah, there you see I'm computing my 1D index from the current column and the row. Because I've made a malloc shard, so I have a 1D array of memory. So I must compute myself for this row and column, what is the rank in the 1D memory. So there I have this kind of computing. I did before already for the pattern, but I must do the same for my index, which is used when I ask for EU or EV. For example, there, the more simpler one, this one, you see, I know that the UV I want to read, it's the current row R plus 1 and the current column C plus 1. So in 1D, I get it using a row plus 1 multiplied by my number of columns plus the current column rank. That's the way to compute it. But as I said, you have utility function in SYCL if you need to do this computation for you. That's the 1D, 2D translation. So back there. So the times I have using ICPX, Intel, or adaptive CPP, quite close as usual, but quite longer than before. And actually what's happening is that it's all automatic. And if you remember the inside view we had before, that was that with the buffers accessors, iteration finished, download result, upload something, then start new iteration, okay? So what we have now with malloc shared, it's a mess because each time I'm accessing this or these values, the system behind say, oh, there I need this value, transfer it, but that's not transfer all the image, just a piece of it. And then at the next step in my loops, it needs the following data. Oh, I miss this data, take a new small part of it, get it back. So all this mess in the input-output, which we don't see because it's automatic, not completely a surprise that it's less efficient that when we transfer the whole image one way or the other. So the next step, as I said before in slides, etc., is that, okay, malloc shared, it's easy. If it's enough for you, if your problem, you don't need more performance, it's the easier way to work. It's even better to do buffers on accessors because it's very meaningful. You see who read, who write. So we are often asked, if I want to write a SYCL code, which should I use between all those ways? The usual answer is you start from nothing, from scratch. Better use buffers accessors because it's the clean way, in one way. You are giving the more information possible to the system. So we would say it's the best. If you're starting from an existing code, the easiest path in general is to move to malloc shared. And if the performance is enough, just stop there. If not, if you want to get more performance from your hardware, then next step would be to move to malloc device, where you control what you create as an area of memory, where, and when you explicit the copy. Because the problem there is that you don't need to explicit the copy, but the automatic way is not so good as it could be. So you know in your problem when you need to copy what, so take the control. And that's what we do with device malloc. So now we will have a look to square device, which is the way to do it with malloc device. And the exercise to try on your side, on your code, is to replace malloc shared with malloc device. That's the easy part. But after that, you will have to add copy commands. Or your computation will be on bad input data. Let's have a look at the square example. Which is square device, SRC. Oh, it's empty, my God. I've lost my file. Oh, I will look if I find it locally. Don't know why it has disappeared. Very strange. Let's try there. But I have pushed everything, so I will probably have to search it in the history of my Git repository. We are looking in square device. We have even lost SRC in square device. Okay, let's try to go back. No. Credible. One year back in time, my God. So here's the code. So as usual, it's in the old style. So queue with GPU selector, etc. I initialize my local array in the host with the input values. Then I'm doing some malloc device. So those pointers, I put a D in the name just to say it's a device pointer. I should not use them locally. It will not work. On the host, they make no sense. They are address which will be only usable in the kernel, in something running on the device. Then there I'm doing the mem copy. If you look at the reference, we will have a look. There's a way to copy with better syntax. But there, what I'm doing, it's a mem copy with the same kind of argument in the same order than the C functions. So the first argument is the destination copy of the copy, which is my device pointer. The second argument is the source of my copy. So I'm asking, I'm taking my std array, I'm calling .data to get the row pointers. Then the size I want to transfer. With this C flavor, I must compute the size in bytes. So I'm taking the size multiplied by the size of a float. And then I'm wait, because if I don't wait and start my parallel for immediately, the copy is not finished, okay? So I must wait for the copy to be finished, then calling the parallel for, when I can use my device pointers. Then I wait, and then I copy back the result locally. So from the output to my output data, local data in the host, and wait again. A way to avoid all those waits, some of them actually would be to make a queue which would be there with the argument to say I want an in-order queue. This would avoid me this wait and this one. But at the moment, I should wait whatsoever, because even if my queue is in order, if I ask copy, compute, copy, I have immediately the end back, and I will do the output before the queue has finished its work. So again, even if I make it in order, the in order applies to what is inside the queue, not my host code. So if I make it in order, I can suppress wait there, I keep this one, or after that, I put a queue.wait before I'm starting to print my result, okay? So try to do that in your code with the Grace code simulation. And perhaps, in the meantime, we can try to find in the reference the alternative to this mem copy I dislike. So let's try to find this. That's the documentation. I'm sorry. For SYCL, we have this reference documentation that you can find in my slides. You have the link. You can find it in the Chronos side. And there, if I try to find a mem copy, where is it? This one. So you see, you have this mem copy, which is a C style, and better, you have this copy function, which is the C++ tag, where you first give the source, the destination, and the number of objects. So prefer this one, of course. And also, if you want to put some data directly on your device, you may call this memcen, which is a C style, or this fill, which is C++ style, doing the same, filling a device array with some numbers.
Sorry, I have a question.
Yeah?
Why the main contribution to the running time is still due to the user?
The user time?
Well, I mean, why the user time and the sys time is so close with SYCL always? Because I would have expected that one of them will be very short and the other one will be...
Yeah, I'm not sure. I have asked it to the experts, the Muppet Show at the last rank. I think they are not sure themselves, from what I feel. How the time, which is especially how the time which is spent on the GPU, is it taken into account in the user time, the sys time, the real time? The real time for sure, we have it. But between user time and sys time, I'm not sure. But Andrea, perhaps Adrien
this
can answer that.
depends on the implementation of the GPU driver. In principle, in an ideal world, which is not the world of GPU applications at all, you would like the GPU driver to stop taking CPU time while GPU work is executing. You know, you just stop doing CPU work and do something else, and this would then not be accounted as either user time or CPU time because you're just sleeping. In the real world, experience shows that GPU drivers can use enormous amount of CPU time in either user mode or kernel mode for, in my opinion, no good reason. But because this is often proprietary software, it's hard to profile it and figure out why it's using so much CPU time. So your guess is as good as mine.
Thank you.
And even on the CPU, perhaps you noticed at the beginning of this practice or last week, but when using adaptive CPP, everything seems normal. But when using the Intel implementation with a single task, we should use mostly one core doing the single task, and we see some kind of huge system, which is quite hard to explain. And especially we see a user time which is greater than the real time. So apparently, for some reason, the Intel implementation, even on CPU, will use several cores. And so one of the things perhaps we'll try this summer to investigate, but quite strange, but okay.
Yeah.
Especially in the Intel implementation, apparently sometimes it can easily use several cores to optimize things that we do not master.
Okay. Okay.
Okay, so let's discuss the solution for the malloc device. Where am I? So we are in step 2, solution. Okay. Step 2, step 3? No, we are step 3 now. Yeah, I think we are step 3. So we start from the main. So my main, how is it? As usual beginning. Oh, yes, for some reason, at this moment, instead of new, I use vectors. We don't care, that's the same, it's better, it's simpler. But it's good for data which stay on the host whatsoever. So I can use a vector. It's better than using the new as before. I call my process images. Then I'm creating here my usual U1, V1, U2, V2 with malloc device. I add this D to the name to remember it's only okay on the device, to be sure I don't try to use them on my host. Perhaps that was the difficult point, is that because I do not buffers, I need to make a new local image in my host with the border to prepare my work. Starting from my image with no border, I put it in a local image with the border. That is the one that I will copy afterwards on the device. So there I'm having this new UH like U host extended image and V host extended image. I'm taking the original ones and put them there with the additional border of zeros. Then preparing my device, my malloc on the device, and then doing all the first copies. I'm copying my U host, V host X on U1D, etc. So starting to copy anything on the device, then wait for it to be finished. I need .data there because I've done some vectors locally. Forget this for the moment. I should have removed them, but they're still there. The process, so I call iterate, and then I made 2 functions, iterate, which is doing the iteration on the device, and download, which is the action of taking the result back to my host. So I'm doing iterate, n times, download, extract, etc. for the number of images I want. So let's have a look at the 3. Those 3s correspond to the malloc device. Let's have a look at iterate. So iterate, receive my device pointers. Work as usual, I think. Just as before. For him, he was having malloc shared pointers. Now it is having malloc device pointers. From the point of view of the kernel, it's just the same. I have this new function download, which is doing the copy back. So from there, for one time, I'm using copy and main copy. So I'm taking from, which there will be called with V1D. This one is the pointer to the V1 device. I want to copy the result to this vector, which is the local VHX vector with the size. Then I wait to be sure it's finished. There I wait also explicitly. And so you see there in my main loop, I'm calling iterate. working on the device, then wait, then calling download, taking the result locally, and doing my usual extract analyze. And that's all. So if I look at the performance, so the clues, you will need to do more extended image on the side, one more. So no need to copy back. Your data is on the device, can stay on it and be used all along the simulation. And what we have in the performance, you see a quite great improvement. Why? But simply, if you look at the insight, what happens, I have scaled, use a greater scale, but basically, when my iteration are finished, I download my image, and that's all. After that, I start my new iteration. There's not these strange things we noticed with the buffers accessors. I don't know why the buffers accessors, they were moving something back to the device, but we know we don't need to. So there we are doing just one copy, the only one we need. And as you see, the performance is, of course, better. So the final big step, which is that normally the hardware, the GPU hardware, is able to, at the same time, compute things and doing I/O with the CPU. The hardware is able to do that. So how to express our problem and our code to get this ideal world where we are overlapping the I/O with the computation? Because there you see, during the download of the data, my computation on the device are stopped. But these new iteration there, they should be done at the same time we are doing the download. There's no reason to wait, actually. So we can fill this gap with computation if we are smart enough in the way we express the problem. So that's the last step, not the easier one. Is try to make some overlapping between I/O and computation. I will first comment the starting point because I made part of the work for you because otherwise it would be too long. So if you look at step 4, starting code, I have already done one thing which is important, is to use the event. Because so to better organize your work, you will need to rely on events. So the starting code, it's the same as before, but with event explicitly. So for example, my call to iterate, it is receiving as input a list, a vector there. You see a vector of event, which I will declare as prerequisite to the computation. So when I call iterate, I can say to it, do not start before this and this and this event is finished. And iterate is also returning an event, which is the event corresponding to its own computation, saying the way for the external caller to know if it is finished or not, if the iteration is finished or not. So how it works, there I have my usual loop. And when I submit my first iteration, I said that depends on prerequisite, which are the ones I received when calling iterate. And when this part is done, after the swap, I will do a new prerequisite collection, which is the current iteration, actually, which will be the prerequisite on the next loop there. So I have this prerequisite vector, which actually contain, at the beginning, prerequisite contain what I received. And after the first iteration, it contained the last iteration I tried, so that each iteration wait the preceding one is finished. And when all my iterations are done, I'm returning the last one as the final event in the loop of iteration. Don't worry, it's written, it works this way. But you see, when you start an iteration of 10 steps, The first time you receive initial dependencies, then after you have started and finished the first iteration, this one begins become the dependency for the next one, etc. And this rolling this way. There I have my download as before, which is receiving as prerequisite actually is the last iteration finished and return itself its own event. And if we look at the process images, here we are. When I call iterate, there's work to be done after? No, not in this case. When I call iterate the first time, the input are an empty vector of events. It's the first one. There's nothing depending on. I've done my copies initial, but I have done an explicit wait. So there I started these ways. Then I call the download. As a prerequisite to the download, I put the event returned by iterate. So that download wait for iterate to be finished, okay? Then I wait explicitly on my download event before I do extract, analyze, etc. And again, I loop on it in the same way. So how to obtain some I/O overlap with the computation? I give you clues. So start from this implementation with the events. Then you will need a new V-array on the device. Why? Because there, if I start there my iteration, I may write on V1D, which is currently downloaded. So I may change the value of V while it is downloaded. So it's not good. So what I must add there is that when I have finished my 10 iteration, my last value of V, I must copy it in another buffer, which will be used by the download. And then I can go on with my next iteration on U1, on V1, U2, V2. So I need a V3, actually, to store my last results so that download can start on it. This time, while I'm downloading, iteration can go on U2, V1, U2, V2. But when they are finished, they will need to store the result in V3, but they must not store before the download is finished, because V3 is under downloading. So you have to set up those, you need to add V3 in the device. And then we have, for the moment, two actions. We have the iterate and we have the download. You must have something that you can call a store or shelf or whatever, which is the action to take the current value of V1 and put it in V3. So you must mix these three actions, and you must set up the dependencies with the events so that the download and the next iteration can start together once the store is finished. One clue which is important, I've not found it in the specification of SYCL, but I noticed that when you start a download, a download event, it's blocking, at least in the Intel implementation. Download is blocking, is waiting actually. So you must absolutely, you cannot do, I start download, then I start iterate, because iterate will wait the download, because it is blocking. So you must do the other way. You must start next iteration before starting the download. So the order, if we are in the middle there, on top of that, there's complexities about how to start, how to finish. But if you are between two iterate, the order is iterate, finish, I start store in V3, and iterate must wait, because until V1 is duplicated in V3, we must not iterate again. So I start store, all the other ones wait, and once the store is finished, I start to iterate again, then download. And this way, and that's the only way I succeeded to implement, perhaps there are other way, but this way, the iterate start and the download start together. try it. But I warn you, it's not easy to make the good connection in the ordering to have the effect. Okay, finished. So one solution, perhaps there are others. So as I said, I'm adding this new malloc device v3d to store my intermediary results, copying anything as before. And actually, to get what I want, I needed to change a little what I'm doing in which order and to make a few things at the end. So what am I doing? First, I shelve what I've just copied. It's a waste of time, but it's a way to start the loop. Then I say iterate with shelves, a shelf event as a prerequisite, and download with a shelf as a prerequisite. As I said, at the moment when you are copying in the device V1 on V3, you cannot do anything else. You cannot iterate because you must not touch V1, and you cannot download because V3 is not ready. So first the shelf, then iterate, then download, because as I said also, when you download, it's blocking, so you must start the iterate before. So the ideal ordering in this problem is to shelve, then iterate and download in parallel, waiting the shelf to be ready. I'm also explicitly waiting after the download, even if it's blocking. It's better this way to be sure I can start the extract on the vHost side. So iterate start, download start. On the side on the host, when download is finished, extract and analyze are done. And I'm back there. And I start again the loop with a new shelf, but the new shelf must wait for the iterate, must be finished, to be finished. And once the new shelf is finished, again, iterate, download, etc. In this ordering, I cannot overlap. But once I'm outside, the last iterate, when I download and extract, analyze, the last iterate was not finished. So to get the good result at the end, I need a few more work on the last iteration after my loop is finished. I must download the last one and extract and analyze, or I will lack the final iterations. And that's all. So let's have a look at the result I got on Cassidy. And so I got these times, so it should be a little better as before. You see, I break the wall of 600 milliseconds. What was the previous time? Yes, you see, I gained about 100 milliseconds, grossly. And the case is that instead of this, I have this. So that's the end of a given iteration. This blue one there, I think, is the shelf, is the duplication, which is on the way on the GPU. And then I start iterate, download. And instead of this about 5 milliseconds, it was in 2 years ago, but it should be similar today, perhaps. But 2 years ago, instead of this gap of all the time in red, I just have this gap between two sets of iteration, which is the duplication of V1 on V3. So of course, I've chosen to run my program with 50 images, 10 steps to increase the effect of I/O, etc. All of this highly depend on your program, on your use case. So there are use cases where it is very important to get this I/O overlapping, and other use cases where you don't care. So only do this kind of game if it is important in your use case, because it must save. It's a big effort to code, so it must be worth for what you gain in your performance.
Okay. If you don't make a lot of copies from the GPU to the CPU, you don't need to overlap.
Yeah.
Okay.
it's important if you are IO bound and you need to not to wait IO all the time.
Yes, yes.
And perhaps I've not tried, but there I'm not doing the HDF5 files. Perhaps it would be important there also because on the CPU side, it takes time to write the files. We perhaps may have even better benefits with this technique there to be tried. Okay, so stopping there. I will just say, don't forget, we have tonight at 6 o'clock, I think, we have a presentation from Thomas Padiolo about Cocos, which is another way to make code running on CPU and GPU. So I invite you very warmly to follow this talk, which is another way to do the same kind of stuff. Thanks to you.